Yeah, hi everyone. This is Prateek. Uh, just a quick check. If you are able to hear me, you can actually respond in the chat section if you are all able to hear me clearly. Yes. So if you are able to hear me clearly, just put a yes or no so that I get to know that you are all comfortable. Sai, Vikas, Mehul, Kritika. Yes, guys. Am I audible to you? Can you please respond on the chat section? Hello. Yes, Mehul, Vikas, Kritika, Sai, do you guys hear me? Okay, perfect. So I think Vikas does respond back. Right. So let's begin with our session today. Uh, uh, so the idea of this session is to actually have an in-depth. Yes. So I think yeah, all of you are able to hear me now. That's great. So the idea of today's session is to have an understanding, for your upcoming exams. We will look at the first chapter, which is chemical reactions and chemical equations. I'll be taking you through a set of slides as well as important points that you should remember while writing the answers. You can always keep posting your queries on the chat window as well as to me personally. And I'll try and address them during the session as well as post the session. Perfect. So let's begin. I'm sharing my screen with you so that you can actually see the yeah. So there we go. Right. So chemical reactions and equations is your first chapter in chemistry, for grade 10th. And it's been a while that we have looked at it. So it's a good idea to really skim through the topics and look at different concepts that are involved in this chapter so that we can understand how do we present them as an answer writing skill as well as the problems that this chapter has, how do we really solve them. So we will begin with understanding what chemical reactions are. So chemical reactions basically chemical reactions basically is a process in which one or more substances get converted into different new substances. Now when we say new substances, they essentially have two distinct properties. One is their chemical properties change and as well as their physical properties change. So when these two properties change, we obviously have a new substance produced, and the process which makes these new substances produced is called as a chemical reaction. The common examples of chemical reactions involve burning gasoline, baking cake at our house, even breathing. So respiration is also a chemical process that we have. Now, what are the different all of these reactions involve two basic categories of substances. So one is a reactant. So reactant is something that is getting changed, and reactants get changed to products. So whatever substances actually get converted, or they lose their original form, they are called as reactants. And what they get converted into are products. So a substance that enters into a chemical reaction is a reactant, and so the substance that is produced by a chemical reaction is actually a product. So now that we understand what chemical reactions are, let's look at what basically yeah. What are the reasons for these chemical reactions? Some of the reasons for this chemical reaction is basically the arrangement of electrons in an atom. We all know that all of these chemical reactions happen because the atoms in a molecule are basically striving to achieve the octet, which is the nearest inert gas configuration. So if you have 8 electrons in your outermost shell, then you are a stable molecule. If you don't have, then you'll either lose electrons, you'll either gain electrons, or you'll share these electrons to form the molecule that is or to form to get the octet and therefore form a molecule for the same. So therefore, what are the reasons of chemical reactions? The first reason is the atoms with a full set of electrons do not form bonds, but the atoms with incomplete set of valence electrons form bonds. Now, a common mistake is between valency and valence electrons. Valency is basically the number of electrons that is either gained, so number of electrons that we gain, that we either lose, or that are shared by the atom to form a bond. Okay, to form a bond. Now this is the valency. Valency is number of electrons gained or lost or shared. Okay, but valence electrons means number of electrons in the outermost shell. Okay, so to outermost shell, so to give you an example, when we say that the number of electrons in the outermost shell is 5, then the valence electrons is 5. Okay, so this is the number of valence electrons, but the valency will be -3. Why -3? Because it needs 3 electrons to be taken in, which will make the chemical bond formed. So remember the difference between valency and valence electrons. It's a common mistake that people interchangeably use this, and you find that there is a problem, in writing an answer. So the reasons of chemical reaction is whether it will form a new bond, and which atoms will actually break their original bond. These two actions may actually make a chemical reaction proceed. Now, what are chemical equations? So, chemical equations are chemical reactions represented by sentences. Okay. So, when I say sentences, they are normal English language sentences, as well as sometimes with mathematical symbols like plus and an arrow. We will look at both of those. So, a chemical equation basically identifies the reactants and products in a chemical reaction. Let's look at how. Whenever a chemical process happens, then one or more substances are changed into one or more different substances. So it's generally a trend, a natural convention where we write reactants on the left hand side and products on the right hand side. So whatever is on the left hand side is taken as substances that are undergoing a change, and products are those substances which will be formed as a result of this change. Now the very process of writing reactants with an arrow to products is what we call as a chemical equation. This equation shows multiple things. Firstly, it shows what changes have taken place. So what substances were originally and what happened as a new substance. The second, it also shows what are the relative amounts of various elements and compounds that have taken part in these reactions. So when we say relative amount, this relative amount can be expressed in terms of weight, or what we generally call as mass. It can also be expressed in terms of volume. It can be expressed in terms of the moles, which is the stoichiometric coefficient. So how many number of particles have really taken part. So all of these together represent what are the amounts that the elements are really reacting with, and in what proportion they are produced as a part of products. So this is one of the merits of writing a chemical equation for a chemical reaction. Let's look at some more properties of chemical equations. So whenever we write a chemical equation, the starting substances, as I mentioned, are reactants, and the end product is products. So when we write these chemical equations, you'll realize that either a single reactant or multiple reactants are separated by an arrow to give a single product or multiple products. Okay. So the reaction can give any number of products, or it can use any number of reactants to give the final outcome. Now let's look at what are the parentheses that we really noted here in terms of G, or you might have different other symbols, for example L, S, AQ. So all of these actually represent the physical state. So there are some important rules of writing a chemical reaction. The first rule is, of course, the chemical formulae for the molecules should be correct. So for example, when we write water, it is H2O, or when we are writing nitric acid, it is HNO3. So in all of these situations, the valency and the correct molecular formula is very important to be written. We have seen how to write atomic symbols as well as molecular formulas in previous chapters. So that's something that we are assuming that we already are aware about. Having said this, when we write these chemical formulas, I'm going to take an example. For example, carbon uh, plus oxygen, O2, gives CO2. A very simple equation that we are going to look at today. So in carbon, we'll realize that we end up writing an S. In oxygen, we end up writing a G, and in CO2 also we end up writing a G. This technically means that carbon is in a solid state, oxygen is in a gaseous state, and carbon dioxide is also in a gaseous state. I'm going to take one more example for the same. I'm going to take carbon monoxide so that we are able to see some more details on the chemical reaction. Everything remains the same except for the chemical formula, where it becomes CO and you write this as gaseous. Now, in this entire expression, if you're writing an arrow, this basically means either an effervescence or a gas evolved. So upper arrows means gas evolved and effervescence, and they are extremely important to write the upper arrows. The second thing that we actually have to remember, so this is an effervescence. Now, effervescence mostly are given out during solutions, but even if you are writing it for products that are in the gaseous form, it is okay to mention an arrow showing a release of a gas. The next thing is a deposition arrow, so where we will find that either a precipitate, etc., is mentioned. So writing all of these symbols of deposition and effervescence are critical. Writing the physical state is critical. So when you say S, it is actually in a solid state. When you say G, it is actually in a gaseous state. Please note that this S and G are written as subscripts. So unlike what you see in the PPT, the subscripts are where G and S you will find in your general text. Uh, AQ generally means aqueous. Aqueous means the substance is dissolved in water. Please note that people generally confuse between aqueous solutions, alcoholic solutions. So when we write AQ, it is especially when it is dissolved in water and nothing else. So if you are dissolving in some other substance like benzene or alcohols and all of those, we do not write AQ. AQ is written only for water solutions. So these are the four symbols that you will commonly find while you write any chemical equation, and all the compounds thus formed are generally shown either released or taken out. Okay, now one more very important aspect is to write the chemical formula beneath the chemical reaction. So for example, here it is a good idea to write as carbon, oxygen gas, in fact you can mention very explicitly, and carbon monoxide gas. So these are the ways that you actually should, this is the way to really write a complete chemical equation, where you not only write the symbols but you also write the names of the particular compounds, and you close all the chemical equations. So that's how you write chemical equations. One of the important factors that I have not yet mentioned is balancing the chemical equations, which will come in a few minutes. Now, for example, this is a chemical word equation where they have mentioned that calcium plus oxygen giving calcium oxide. The plus sign here means it reacts with. So at any point of time when you have a plus, sometimes you will find that calcium plus oxygen plus heat, so which means that heat is actually taken in on the reactant side. And if the same heat is written on the product side, it means that heat is evolved. So the plus sign here actually means it reacts with, whereas the arrow means that it yields means it produces. And it also shows the direction of the reaction. It means that it is going from the reactant side to the product side. So anything that is on the arrow side is your products, anything that's behind the arrow sign is actually your reactants. Now let's look at how do we write a formula equation in much more detail. So firstly, we write all the symbols, and once we have written the symbols, the subscripts actually mention what valencies you have. These are small things, but the common mistakes are the subscripts are sometimes confused with coefficients. So that is something that you have to avoid by writing answers. The subscripts are a part of the molecular formula, whereas coefficients are not. Coefficients show you the amount of the molecules that are essentially available for the chemical reaction. So this is something that we have to keep in mind. So whenever someone gives you a word equation means that you are generally given an equation where you have calcium plus oxygen written as calcium oxide or something like that, then the idea is that you write the symbols for it. For example, here calcium is written as Ca, oxygen as O2, and calcium oxide as CaO. Now, let's look further. Let's write a few chemical equations that we have for the statements that is given here. So the let's say the problem is silver nitrate reacts with copper. Now you will see that there is a one or two mentioned here. These are oxidation states of that particular element. Okay. So for example, when we write silver, so the idea is that silver 1 means silver with a valency of 1 or oxidation state of 1. And when we write silver nitrate, nitrate obviously has one valency, so it has to be AgNO3. Now, the practice problem mentions that silver nitrate is reacting with copper, so Cu, to form copper nitrate, that is CuNO3. Now, please note copper nitrate, copper can also be of one oxidation state, in which scenario you end up getting a molecule of CuNO3, but it can also be of two oxidation state where you have Cu2, which ends up giving CuNO3 twice. Okay, NO3 twice, right? So both of these are some important considerations. So if 2 is given, please don't choose an oxidation state that is not that is not relevant to us. So in this scenario, what we'll do is we will choose CuNO3 twice, and we'll write our chemical equation. So this will be CuNO3 twice. Now plus it says silver, right? Now please note, in a word equation, nothing else about the physical state is mentioned. So it has to be assumed what of these physical states would be. There are multiple ways to assume this. One is most of the equations are actually mentioned in your text. So if you just go through these equations, I think that's a good repository of what equations you should know about. But apart from that, another clue, for example, I want to mention here is AgNO3, when it is getting displaced by copper, obviously has to be in the dissolved form. So the best idea is to write an aqueous here. Copper, obviously copper is in its atomic form, so therefore it has to be a solid. CuNO3 now, because it has been formed, you'll find that this is either in the dissolved form or it could be a precipitate as well. But since Ag is getting released, so I would consider CuNO3 in the aqueous form and silver in the solid form. So you will find that arrow here will make the best case. So silver has to get deposited, and it has to be written as a solid. So this is one of the very important aspects that we have to remember while we write a chemical equation. Now let's look at hydrogen peroxide, where we have H2O2. Now H2O2 is going to decompose into water and oxygen. So all that has been given to us is that there is hydrogen peroxide which decomposes into H2O plus O2. Now, please note again, in the above equation, we have not yet balanced. So I'm just holding the balancing thing for a few more slides, so that we actually come to understanding how we really do that from either a trial and error basis or some other equations. Okay. So now when we are looking at H2O2 as it decomposes into water and oxygen, you'll find that H2O2 is an aqueous solution. Water, this we will write as liquid, because there is nothing like water dissolved in water, so you write this as liquid. And oxygen gas would be evolved, so you write an arrow and you write this as gaseous form. Now one important part of this is, it's also a good idea to write the names of chemical reactions beneath it, saying that this is hydrogen peroxide, this is water, and this is oxygen gas. So this is a complete way of writing a chemical equation, where you have written the states, you have balanced the chemical reaction. Here again, it is still not balanced. I'm coming there. I've repeated that twice. But balancing the chemical reactions, writing the arrows, writing the names of the compounds, all of this has to be taken care of. Uh, so coming back to our understanding of chemical equations, now we will look at what do you really mean by balancing chemical equations. So a typical question that comes in balancing chemical equations is that why do we balance chemical equations? It follows from our understanding of law of conservation of mass. So basically, whatever has been put into the solution has to come out, because the mass has to get conserved. So coming from the conservation of mass dynamics, balancing of chemical equations is critical to write a completely fully explained chemical equation. So now let's take our all the examples that we have done. For example, when we wrote AgNO3 uh, plus Cu to give CuNO3 twice, because we were mentioned as Cu with a two oxidation state, plus Ag. We had also seen that AgNO3 was aqueous in nature, Cu was solid, CuNO3 further is aqueous in nature, and Ag is solid. Now, in this scenario, we find that NO3 is not balanced. So the first thing that we'll do is we'll balance NO3 to put it twice here. The moment I balance NO3, you'll realize that silver is now in excess. So you put 2 sign here. So, and here you will write a deposition symbol. So this is actually a complete chemical equation. Of course, you have to write the names like silver 1 nitrate. It is a good idea to mention oxidation state as many times as possible. It gives a very clear cut idea to the reader what compound you're talking about. This is copper. You can mention just as copper. You can mention this as copper 2 nitrate, and you can also look at Ag as a solid deposition. Okay, so all of this actually will help you in understanding the chemical reaction. Yeah, just a few quick second. Right. Now, coming back to balancing this chemical reaction, we know that matter cannot be created or destroyed. So, whatever number of atoms we have here, all of those atoms have to be present in the product side. So, and now there are a few rules that we would follow in balancing this chemical reaction. For example, so basically the mass of the reactants and the products has to be same. That is why we balance chemical equations, and for this mass to remain constant before and after the reaction, the number of atoms has to remain constant, because we know that the mass is proportional to the number of atoms, the quantity of atoms that we have, and therefore balancing both on the reactants and the product side will balance the chemical equation automatically. Yeah. So let's look at a few more examples. Uh, let's say we have 4 hydrogen and 1 carbon in one of the chemical reactions. Then we will need 4 hydrogens and 1 carbon on the other side of the chemical reaction as well. So this is important to have the same number of atoms on both sides of the reactants and the products. Now, how do we go about this process? Because if we have a systematic idea of balancing a chemical reaction, then it would be ideal for us to do that for any chemical reaction. So here are a few examples or steps that we can use to balance chemical reactions. So the first thing is, whenever we write a chemical equation, determine the reactants and products, which would be pretty obvious from the arrow sign. Now, whatever other reactants are written on the LHS, as I mentioned, the arrow actually means the yields, or as I mentioned, the what is produced, and products on the right hand side. Now, when we are balancing, the third step we would generally come to is to count the number of atoms on both the sides and see which atoms are deficient. So, for example, in our case here, which is the simplest of the examples, H2 gaseous plus O2 gaseous, giving H2O liquid. Yeah, and this you will find that we have hydrogen which are two on this side and two on this side, but oxygen are two here and one here. So definitely we need to balance the oxygen. So we would put two here on this side so that oxygens are now balanced, but that makes hydrogen four. So to balance hydrogen on the other side, you would multiply here again by two, which will make hydrogen into four atoms. So now we have four atoms, two atoms, four atoms, and two atoms. Now everything seems to be balanced. A few key things, so this is a very basic example that we are looking at. But having said this, there are some important points that we have to really remember. Firstly, balancing a chemical equation means only balancing the coefficients. Okay, so we are only going to balance the coefficients, never ever touch the subscript. If we are touching the subscript, it means that we are actually changing the chemical formula of the molecule, and therefore a different molecule is what we are referring to, right? Now, the second most important thing is, whenever we write this subscript, always remember that all of these subscripts are in the lowest possible ratio. For example, another way of balancing this would could be 4H2 plus twice O2 giving 4H2O. Okay. Now, if you really see, there are four hydrogens here, eight hydrogens here, and there are eight hydrogens here, and there are actually four oxygens here as well as four oxygens here. So it seems that this is a balanced chemical equation, but the chemical equation is not in the lowest ratio, and therefore this would not be technically the best way of writing a chemical equation. So when you write a chemical equation, write them in the lowest possible ratio, as well as balance this equation using the coefficients that you can have as minimal as possible, and do not change the subscripts, only change the coefficients. So this is a quick way of balancing a chemical reaction. Of course, trial and error method is the best to do that. We'll look at a couple of examples now. So for example, we have calcium plus oxygen giving CaO. So if you really see this, you'll realize that it is not in balance. There are two oxygens on the left hand side, but only one on the right hand side. So without changing the subscript, so you don't go tomorrow to do it as CaO2. That would be a, just changing the molecule. In fact, nothing of that sort really exists. Maybe some superoxides, but that's not the way to do it. So what we really do is we put in a coefficient around calcium. So you'll realize that we will write this as twice of Ca. Sorry, yeah, you'll write this as twice of Ca and twice of CaO. And therefore, now you find that both the oxygens are taken care of, as well as calcium also are taken care of. These are called as stoichiometric coefficients. In stoichiometric coefficients, or in simpler terms, it's simply called as coefficients, or in simple terms, it's only called as the coefficients of the reactants on or the products. So this is a quick way of balancing chemical reaction. Now let's look at some more equations. Now, let's say another example is given to you about methane plus oxygen giving carbon dioxide plus water. You'll find that all of these can be written as chemical formulae. For example, CH4 plus O2 gives CO2 plus H2O. Now, you'll realize that is this balanced or not? The carbon, if you really look at the carbons, the carbon is 1 1 on each side. Oxygen is, yeah, there are two, here there are three. Hydrogen, here there are four, and there is only two hydrogens here. So we will need to balance this chemical reaction, and therefore we will start balancing by looking at the number of atoms found in both of these. So for example, let's look at C carbon first, CH4 plus O2 giving CO2 plus H2O. So you will realize that the carbon seems to have been balanced. Yeah. But let's you can begin with any of those. You can either begin with oxygen or with hydrogen. Here it seems there are four hydrogens, so I will put in two more hydrogens here. So this takes it two into two hydrogens become four. Let's look at the oxygens. There are two oxygens here and two more here, so there are total four oxygens. If I simply multiply this by two, I end up getting four oxygens here as well as four here. So all of these make sense, and we have now everything balanced: carbon balanced, hydrogen and oxygen balanced. There's another way to do this is you can actually make a table. Okay, an iterative table where you can actually put for example, all the atoms to begin with. So you say carbon, you say hydrogen, you say oxygen, and you can always put them into reactants and products. Okay, so you can make two partitions to them and keep on writing it one by one. So for carbon, you can write this as one in reactant, one in product. For hydrogen, to begin with, there were four and there were two. For oxygen, to begin with, there were two and there were three here. So you firstly, this is cleared, so you don't look at this. Hydrogens, there are four here, so you simply make it four here, so you multiply by two. When you multiply the hydrogen on the product side by two, you suddenly realize that oxygen is two on this side, but here it becomes four. So as oxygens become four, now you know what to do for the oxygen on this side, so you can simply multiply this by another factor of two on the reactant side, and you will end up getting 4 4 4 4 and 1 1. So this is another quick method. I think it's also a good method that you can quickly draw a chart, a box type of a system where you can simply start balancing these chemical reactions. Sure. Now, from there, let's look at some practice problems. So we had seen water, getting balanced, but we'll also see maybe C2H6 O. So this could be an ether, this could be an alcohol. So both of them, C2H6O plus O2, giving CO2 plus H2O. So as we had mentioned, quickly just write, let me use a different color for that. So what I'm going to do is I'm going to write the carbon, the hydrogens, and the oxygens, any way of the table, either horizontally or vertically, hydrogen and oxygens. So carbon, I know that there are two on the reactant side, whereas there is only one on the product side. For hydrogens, there are six on the reactant side, but there are only two on the product side. For oxygen, you will see that there are three on the reactant sides and there are three on the product side. So it seems that the oxygen is balanced, but there is a huge gap between uh, uh, carbon and the hydrogens. So let's look at first the hydrogen, because this gap seems to be pretty large. So since there are 6 and 2, we would be happy to really multiply this by 3. So the moment I multiply this one by 3, you realize that the hydrogens immediately gets balanced. It's a 6-6 balance. The second thing that you can look at is what has happened to the oxygen. So the oxygen now are 5 in number on the product side, but just about 3 in number on the reactant side. So there needs to be something done, and the carbon is also to be balanced. So what we can go for the next is to really balance the carbon to make it 2 2 by multiplying the product side by a 2. So now you have carbon as 2 on both the sides, but the oxygen has changed. So hydrogen has not been touched at all, but oxygen now on the reactant side is still 3. On the product side it is 4 plus 3 7. So a good way to do this is, now that we have 7, you simply multiply the entire right hand side on the oxygen side by a 7 by 2. So now that we have 3 here, out of 3 you take out 1, so you need only 6 oxygens here, which can be multiplied very well, multiplied by 3, and you can get an oxygen. So now let's look at what has happened to the entire chemical reaction. Do we have 2 carbons? Yes, we do have 2 carbons. Do we have 6 hydrogens on both the sides? Yes, this is 6 and this is also 6. So we have 6 hydrogens. Now let's look at the oxygen molecule. We have 6 plus 1 7. This is 4 plus 3 7. So we do have 7 oxygen molecules. So the only thing that we really need to think about was, how do I balance the oxygen? We had an odd situation where it was 3 and 7. Of course, if you have just put in a 3 here, we already knew that one oxygen is stuck with the C2H6O. So I can remove that oxygen. I needed 6 oxygens more. So the moment I multiply it by 3, I would end up getting oxygen as 6 atoms. Okay. So this actually balances the chemical reaction, and you will realize that the same is actually mentioned as the solution, right? Now let's look at maybe a few more. Yeah, so all of these are practice problems, as I do along the side. I would also request that you all have and all have a look at these solutions and try to balance them. Let's look at zinc plus HCl, giving ZnCl2 plus H2. Okay, so here we again have uh, we again have zinc balanced already. We have HCl and chlorine not balanced. There are two hydrogens here, only one hydrogen. So let me multiply by 2. So I have two hydrogens here. Now let's see about chlorine. So you have two chlorines here and two chlorines here. So everything seems to be balanced, and the balanced chemical reaction simply needs 2 at the HCl side. Let's look at Al plus O2 giving Al2O3. Okay, so Al plus O2 gives Al2O3. Now in this scenario, I need 2 aluminum, so I'm going to just put in 2 here. There are 2 oxygens here and 3 here. Basically, I need 3 by 2. I need this as 3 by 2. But the moment I do this as 3 by 2, it's actually in the fractional form. So a good way to do this is multiply the entire equation by another 2. So you can write this as 4Al plus 3O2 giving twice of Al2O3. Okay, so for aluminum is what we have had. This is 6 oxygen. You will find that 4 aluminum again is here and 6 oxygen is here. So this seems to be a balanced chemical reaction. Let's look at Al plus CuSO4. Yeah, let's look at aluminum plus CuSO4 giving Al2SO4 thrice plus Cu. Now you'll realize there that aluminum itself is not balanced, SO4 is not balanced, even just the copper seems to be balanced. Now, so let's begin with balancing the SO4. Why? Because it seems to be the furthest apart. So SO4, there is only one here and there are three in here. So what you can do is you can multiply by 3 here. So that means that SO4 gets balanced. The moment you have 3, the copper also turns out to be 3. So copper also seems to be balanced. Now there are 3 copper here and 3 copper on the product side. SO4s have been balanced. Now only thing that is remaining is aluminum, and you can do that by putting up a twice of aluminum here. Okay, so this actually covers all the segments of balancing the aluminum reaction. Now let's look at the lithium H2O reaction. So we have Li plus H2O giving LiOH plus H2. Now, in this scenario, the lithium is balanced already. We find that hydrogen is twice here, and there are 3 hydrogens here. So something has to be done about the hydrogen. Oxygen also seems to be balanced. So all we need to do is balance the hydrogen, and for that, whatever else is required, we will have to take that and balance as well. Now, there are only 2 hydrogens here, but there are 3. So let me try and put in a fractional balance. So that this is another good way to do that. This is just to be done mentally, not really in the exam, because to get in by a trial and error method, sometimes it might be difficult. So since there are 3 here and there are 2 here, a good idea is to multiply this by a 3 by 2, so that this 2 and 2 cancels out, and you actually have 3 oxygens on both the sides. Now, but since we cannot do and we cannot play with the subscripts as we have mentioned, what we generally do is we'll multiply the entire equation by a 2. So you end up getting 2 lithium plus 3H2O giving twice of LiOH plus twice of H2. Now let's look at if we have really got our solution. So we have 4 hydrogen here and 2 hydrogen here. So total 6 hydrogens are present. There are also 6 hydrogens here. Lithium also seems to be balanced. Oxygen, there are 3 here, but we have only 2 oxygens here. So oxygen is still not balanced. So we need some more balancing to be done here. So for oxygen to be balanced now, there are 3 oxygens here and there are only 2. So uh, okay, so twice. So let's try and balance the oxygen for one more time. Yeah, so maybe we could just use a 2 in here, and that should satisfy. So how many hydrogens do we have? 2 and 2, 4. uh, okay, so the other way is also to write this as Li plus H2O actually gives out LiOH plus H plus. This is the first one, and then if we need to form an H2, we will have to have 2 hydrogens, so the entire reaction can be multiplied by one more time. So LiOH comes in one more here, and you have H2O plus Li. So if you simply add these two reactions, you'll end up getting twice of Li plus twice of H2O gives twice of LiOH plus H2. This seems to be a very balanced reaction. Let's look. 2 into 2 hydrogen is 4. Here also we have 4 hydrogens. We have oxygens that are also balanced 2 2, and we have 2 lithiums balanced. So sometimes when you don't get it by a fractional method, this is a good idea to actually find out what's happening inside the reaction. So I know that when LiOH is reacted, it will give out a hydrogen, and I need 2 hydrogens to basically make one H2. So this is another way to really do it by a trial and error method. So there are multiple ways that you can actually balance the chemical reaction, and as you balance these reactions, you'll realize that this is also a skill that you will need to develop. And one way is, as I mentioned, so there are couple of ways that we really saw. One way is simply writing the number of atoms on both the sides and looking to balance them. The second is actually to write partial reactions, so you can write a partial reaction here and try and balance them. The third way is to simply put in numbers, maybe put with a fractional one, and you can do that as well. Yes. So Ishan has been commenting, sir, yes, we can do 2 Li and 2H2. That's right, Ishan. That's a good point. But the idea is that, do we have a schematic method to do this? Can we really program this and have a straight method to do this? Yes, we do have. So we have seen at 3 different methods. One, by writing number of atoms and trying to balance them. Second, writing in a fractional form. Sometimes when you're stuck in a fractional form, then the third method is that you actually see what are partial reactions and try to balance them. So this is one quick method. of balancing. Please note, in this reactions, the reactions are not complete until you write the state. Liquid here, then this is also aqueous, and this is actually gaseous, to show an arrow and to write the names of all the molecules at their bottom. So that completes the reaction. At some point of time, you'll also see that you write a heat here, or you'll write temperature simply 300 degrees Celsius. That gives us some additional information about what conditions do we really have to do. Ruchir is mentioning what was the last method. So the last method, Ruchir, is I'm going to write that again for you, just so that you have a bit more clarity, is what really is happening in the reaction. So for example, when we write Li plus H2O, I know that when I say LiOH is happening, there must be a hydrogen that must be available, right? Because out of H2O, which is HOH, if I take out an OH, then we have a hydrogen remaining in the solution. So where does that hydrogen go? Now I know that this hydrogen is the one that is forming H2. So I need one more hydrogen to come out. So maybe this reaction is happening twice. So I can write it one more time, saying that Li plus H2O gives LiOH plus another hydrogen. And then I can add them up to write this as twice of Li plus twice of H2O, giving twice of LiOH plus H2 gas. Okay. So the last method is where we are writing this as partial reactions. Yes, so we write them as partial reactions. Basically, essentially, really trying to find out how the ions are getting exchanged inside the reaction itself. What we are also going to see is the type of reactions, which is a part of our theory for forward. So that's the idea to really use in while we are balancing these chemical reactions. Sure. So let's look at some more practice problems where we are looking at aluminum reacts with oxygen to produce aluminum oxide. So you can simply write this as Al plus O2 giving Al2O3. We have already balanced this previously. We know that we write this as 3, and the moment oxygen is written as 3. This is as not 2. Sorry. So this comes out to be twice and twice here. So this would be 4 aluminum. So 4 aluminum plus, so we have 6 oxygen here, we have another 6 oxygen, and we have 4 aluminum. So this actually does work. There are a couple of questions. So what is the state of Al2SO4 thrice in the third one? The state, see, anything that is actually a dissolved solution would always have an aqueous state. So for example, in Al2SO4 thrice, this would be in aqueous form. A key to really know this is basically to see what its other product is. Now, since copper is the other product, we are sure that copper would be in the solid state and would be deposited. So if copper is getting deposited, then obviously the second component that it has would be a dissolved salt, and therefore this should be in the aqueous form. So Al2SO4 thrice is an aqueous form. When we'll understand the higher chemistry, we'll also realize that which sulfates and which phosphates are soluble. So the aluminum sulfate is the soluble one, and therefore you'll find that this is in the aqueous form, whereas copper is in the solid form. Right. So good question. I think that explains this part. And then let's look at some more practice problems. We have already seen aluminum and oxygen one. Let's look at sodium nitrate and calcium chloride, producing sodium chloride and calcium nitrate. Another quick, easy one. So we will write this as sodium nitrate, NaNO3. NaNO, yeah, so this is NaNO3, sodium nitrate, giving plus calcium chloride, CaCl2, giving NaCl plus calcium nitrate. Now please note, calcium will retain its +2 valency, and therefore it is CaNO3 twice. Please do not make mistakes in writing the molecular formula. While we write the molecular formula, the valencies have to be matched. The valency of NO3 is -1, whereas calcium is +2. So this ends up being CaNO3 twice. So when you write this, now obviously you realize that sodium is balanced, calcium is balanced, but NO3 is not balanced, neither is chlorine balanced. So obviously we need to balance this out. We have twice of NO3, so that gives us a hint that maybe putting 2 here might balance nitrate group, which is NO3. So obviously now sodium is not balanced. Sodium is twice here and only 1 here. So I'll put in a 2 here. This automatically balances the chlorine part. So the chlorine is now balanced with 2 chlorines on both the sides, 2 sodium on both the sides, and 2 nitrates on both the sides, whereas calcium 1 on each side. So this is sodium nitrate getting balanced. The last reaction is slightly tricky, and a few of you had a question on how come nitrogen forms so many compounds. So I've involved a question on nitrogen as well. So you can see the question mentions that dinitrogen pentoxide. By the very name, we know that when we say dinitrogen, it must have twice of nitrogen, and pentoxide means it must have five oxygens. This, when it reacts with water, gives nitric acid. This is what is being mentioned inside the yeah, in the chemical reaction. Now you'll realize that obviously there are two nitrogens here and only one nitrogen here. So one idea is actually to multiply that with a coefficient of 2. Once it is multiplied with a coefficient of 2, we have twice of hydrogen. So hydrogen seems to be balanced. Let's look at the oxygen. We'll find that 6 oxygen are here, and here also it turns out to be there are the 6 oxygens, and therefore this chemical reaction is balanced pretty easily. Now, one of the important things that we will notice in this chemical reaction is that as we actually write the chemical reaction, and the most common doubts are how we are going to write the molecular formula of nitrogens. So you see, nitrogen actually has 5 electrons in the outermost shell. There are multiple ways that nitrogen shares these 5 electrons with other atoms or other elements. So the oxidation states that nitrogen shows are varied. So you have NO2, you have NO3, you have NO, then you have N2O5, right? In all of this, you will realize that nitrogen shares oxidation states right from -3 to up to +5. Okay, so there are multiple oxidation states that nitrogen can show in, and therefore it is what shows you the multiple various oxidation states of nitrogen. One key thing that we need to remember here is that nitrogen shares electrons, without really sometimes completing the octet as well. That's again beyond the scope of our current discussion. But for example, when you look at NO forms a nitrogen double bond with oxygen, and you will realize that here the octet of nitrogen is not really clearly completed, right? So you'll realize that so there are multiple compounds that nitrogen is able to form when we understand its orbital configurations, which makes us get different compounds. So this is a quick look at how to balance chemical reactions and some problems on chemical reactions. Now, let's look at writing a complete chemical. We have already seen this, but just to show you an example, I have mentioned, methane plus oxygen gives CO2 plus water. You will realize that it's a balanced chemical reaction with its states completely written. Since the entire reaction is gaseous, I don't need to write any arrows of evolution. The only thing that I might want to add is writing the names of these molecules. So, for example, I can mention, sorry, yeah, for example, I can mention this as, yeah, as methane. I can mention this as oxygen. Oxygen gas. In fact, you should write it completely oxygen gas. Please do not lazy around writing the chemical molecular formulas, because these molecular formulas themselves will make sure that you get your full marks. This can be written as carbon dioxide gas. Yeah, carbon dioxide gas, and you'll have water. Now, please note it is a water in the gaseous form, so it's a good idea to write it as steam. Okay, steam, right? So all of this is important to mention on the chemical reactions wherever necessary. Good. So now let's go to the next part of this chapter. So this chapter, you will see, is divided into 4 different parts, right? So just to give you a quick summary, the first part actually deals with understanding. So you should have a chapter map before you whenever you are studying this chapter. The first part of this entire chapter deals with what are chemical reactions and how to write them. Okay, chemical reactions as well as writing chemical equations. Okay, so that's the first part of this chapter. Okay, the second part of this chapter is actually mentioning about what are the balancing of chemical reactions. That's a very important part. So I tend to write it separately from chemical equations. So the balancing part, balancing chemical equations. And the third part of this chemical reaction is actually the of the entire chapter is actually what are the types of different reactions. So you can write types of chemical reactions. Okay, and what are their examples, etc. And the fourth part of this chapter is where you will study about a typical few reactions. For example, you have corrosion, or you have rancidity, for that matter, all of those parts, right? So these are the four major, you can say, components of this chapter. So while you study, please remember that you block your components in these four factors and you actually study them effectively. Now let's look at so we have finished the first two components of this chapter. Now we are going to look at the third component, which is the types of chemical reactions. So let's look at what are the different types of chemical reactions. The first one is what we call as combination reaction, or simply synthesis reactions. So we call them as when two products get together. So let's look at a few combination reactions. So for example, when you have A plus B giving AB, you will call this as a synthesis reaction. Okay, so in this reaction you will find that two basic elements are coming together to give you a bigger element AB. Okay, so this is where we say that two or more reactants come together to form a single product. Okay, so that's a synthesis reaction. The second is the product in synthesis reactions, or what we call as combination reactions. Okay, the product is more complex. So in combination reaction, you'll find that the product is generally a complex product than its elements. So AB, for example, is the complex product that we are talking about. When we say complex, it basically means that there are multiple elements that are together forming the compound rather than simplistic ones. So for example, our very common example is H2 plus O2 giving H2O. So you'll realize that H2 and O2 are basically elements, and H2O is actually a complex molecule, right? So H2O is a complex product. So in synthesis reactions, products are always more complex than their reactants. This we call as the combination reactions. And more than two or more substances would combine to form one new substance. Okay, the general form of these reactions is either an element or a compound plus another element or a compound will always give a compound. Okay, please note I have not written element here because it does not form an element, it forms only compounds. Okay, so an element or a compound plus another element or a compound can give you another compound. Okay, so that's the general form of the combination reactions. Okay, and that's what is required to form combination reactions. Now let's go further understanding these combination reactions. There are a few examples that you can see on the screen. So first example is you have ammonia plus HCl giving NH4Cl. So this is basically, you don't even need to balance this, it's already a balanced reaction. Most of the combination reactions you will find that are generally technically already balanced. The second is a CaO plus SiO2 giving you a CaSiO3. Okay, this is another balanced chemical reaction. The other one is water plus oxygen giving H2O2. This is hydrogen peroxide. This is not balanced without really adding a coefficient 2. So in some cases you'll have to balance them, but you can realize that you have hydrogen and oxygen giving out a molecule hydrogen peroxide, which is actually a balanced molecule, which is balanced by using a coefficient 2 on both the sides. The next one is actually sodium plus chlorine giving you NaCl. So these are all different combination reactions. Okay, and you will realize that CO2 and H2O giving H2CO3 is another example. There are going to be multiple examples. If you see all of these reactions are of the type A plus B giving AB, you'll realize that A or B most of the times are either an element or a compound. For example, in H2 plus O2, A and B both are element. In Na and Cl2, they are again in the elemental form. But if you realize in NH3 and HCl, they are in the compound form. But if you look at AB, they are all compounds. Okay, they are all in the compound form. They are all in NH4Cl, CiO, CSiO3, H2O2. They're all complex compounds. Okay, so that's the way that you can actually look at different combination reactions. Now let's look at the next type, which is the decomposition reaction. So decomposition, by the very word, it means that it is breaking down into smaller parts. Okay, so essentially when you are looking at a compound which is very complex, it's basically a reverse of what we did in combination reaction. So AB going to AB plus A plus B is actually a decomposition reaction. Okay, so now here you will realize that a single compound actually breaks down into two or more compounds. Okay, It is of the form where a complex substance gets down to simpler elements or simpler compounds. Let's look at a few examples of decomposition reactions. Some characteristics of decomposition reactions is when a compound breaks apart, it decomposes into simpler substances when energy is supplied. So this is an important factor, that supply of energy actually gives you decomposition reactions. Now, energy might be supplied in multiple forms. It can be supplied in terms of heat, in terms of light, in terms of mechanical shock or electricity. So there are multiple ways that you can actually have the energy being supplied. But as this energy gets supplied, you will realize that the substance breaks down into simpler substances. Here is a general form of these reactions, that a compound actually gives two or more elements, or two or more compounds. Okay. Let's look at a few examples. So you'll see that most of these examples are actually the reverse of your combination reactions. So for example, when you have H2O2 giving H2O plus O2, we had seen this in the combination reaction where H2O and oxygen had given you H2O2. Then we had also looked at CaCO3 giving CaO and CO2 earlier. So this is just a reverse reaction of what we have seen earlier again. So you'll realize that this is a decomposition reaction where a complex compound is actually giving two simpler compounds. Here is one reaction where a complex compound is actually giving elemental forms. So there are multiple reactions that you can see, which are of the form of decomposition reactions. Now let's look at the third major type, which is the displacement reaction. Sometimes it's also called as single displacement reactions. So when we are talking about single displacement reactions, only one element displaces another one in the compound. So you'll have a general form of A plus BC giving AC plus B. The way that you write these reactions is, you actually, so if, let's say someone asks you, write the properties of a decomposition reaction, it's a good idea to mention that they have a general form of A plus BC giving AC plus B. You'll realize that in this scenario, you'll find that one element and a compound gives another element and a compound. Okay, so please note that element is something that is very critical in this scenario. You will find that zinc with AgNO3 is giving you Ag plus ZnNO3. So here you will find that one metal is displacing other metal from the compound. Okay, so these are the important factors that we have in displacement reaction. Now let's look at some more forms. For example, in the same displacement reaction, when we have single displacement reaction, we have A plus Bx giving Ax plus B. One element and one compound are basically get exchanging one more element type. Now, most of these are generally ionic compounds. That's a very important thing that we need to really look at, that most of them are of the ionic form. Now, let's look at some more examples. In single displacement reactions, what really guides this entire process is the reactivity series. We will be looking at reactivity series again in metals and non-metals. But just for your understanding, I've put it here as well. I've also given you an acronym to really remember that. So one of the acronyms that I'm putting on the screen is, please stop calling me a careless zebra. Instead, try learning how copper saves gold. So if you really look at the first letters of this entire sentence, you'll find that potassium, sodium, calcium, magnesium, aluminium. Generally there is a confusion between the carbon here and copper. So please note that carbon is always on top of copper, and calcium is the topmost. So when you say col and car, that's something that will give you a hint of it's calcium and carbon. Okay, so don't make mistakes when you write calcium, carbon, and copper. Calcium is at the topmost of the reactivity series, then there is carbon, and then there is copper at the bottom. Okay. Now, also another common mistake is sodium is, S is not really recognized directly as sodium. Generally, the first thing that comes to our mind is Na, but please note that S is sodium here. Of course, I mean, this is something that is not really mistaken that commonly, but the bottom one is silver. In fact, there is platinum and gold below, platinum and palladium below gold. That also you can really look at. So in all single displacement reactions, someone who is more reactive displaces someone who is less reactive. So for example, in this scenario, you can see that Mg and CuSO4 we are talking about. So Mg is above copper. So therefore, Mg will displace copper and remain in the solution. Please note that anyone who is higher in the reactivity series would love to be in the aqueous form. So this is a trick that I can share with you, is that anyone who is in the higher in the priority would love to remain in the aqueous form. And when I say in the aqueous form, basically in the salt form. So if someone has to stay in the salt form, it has to form a compound and really displace the other element. So copper is actually deposited in this equation, which is a single displacement reaction. This reactivity series is something that you'll need to memorize, and hence I have put in an acronym also for you, which you can make use of. Now there will be predictive questions that can be asked to you, so as to say that predict whether or not this reaction will occur, predict what will be the products. So for example, Cl2 plus Ki, whether this will happen or not. So you'll realize that Cl2 plus Ki does react to give KCl plus I2. Okay, in this scenario, you will find that iodine is displaced by chlorine, so basically potassium will stay in the form of product, because potassium is actually a very highly reactive element. So whether it is metals, all metals replace other metals or hydrogen, and there could be non-metals which replace non-metals as well. So all of these are important. Remember, when simply it is given with acid or water, you will realize that metals will give out, displacing all the hydrogens in the series. So this is a quick look at single displacement reactions. Now let's look at double displacement reactions. The basic principle of displacement remains the same, whether it is single displacement or double displacement. The idea here is, but that two compounds react, and two compounds basically end up exchanging atoms between themselves. So for example, AB plus CD has been given AD plus CB. So the general form of this reaction is written here. So a couple of points that you can write when you are asked a question about what kind of reaction is this, is that firstly you can write the definition, you can write its general form, you can also write it in terms of elements and compounds, and then the last one could be an example. Sometimes you also can write a reason around it. For example, you can mention that the reactivity series is what is followed during this displacement reactions, and therefore the compounds or elements end up displacing someone else from the reaction. So that's a quick look at double displacement reaction. Let's also look at what kind of compounds actually form double displacement reaction. So you'll realize that it mostly has to be an ionic compounds of two different compounds that exchange ions between them. uh, Yes. So Ruchir is asking, is non-metal replacement also called as displacement reaction? Yes, it is called, Ruchir. Anywhere any element is displaced, so anything that has a form of A plus BC giving AB plus C is a displacement reaction. Okay. So remember the form. The form is core to any displacement reactions. So yeah, so that answers your question. Now coming back to our double displacement reaction, you'll find that atoms or ions from two different compounds can replace each other, and of course, how do we identify that there are two compounds as reactants and two compounds as products? So this is always one of the key factors whenever you look at double displacement reaction. I have mentioned a example here, which is CaCO3 plus HCl giving CaOCl2 uh, plus sorry, CaCO3 plus HCl giving CaCaCl2 plus H2CO3. So this is one common example. You'll realize that here calcium has replaced hydrogen and taken over chlorine. So it becomes CaCl2, and CO3 has gone with hydrogen to form H2CO3. So this is an example of double displacement reaction. Now let's look at a few more important reactions. Yeah. AgNO3 plus HCl giving AgCl plus HNO3. So this is another important reaction that we have mentioned. So you'll find that the silver is actually going with chlorine now, whereas hydrogen takes in with NO3. Now another common mistake that people do is they don't realize that which are the elements that you should actually have to form the compounds. So for example, whether it should be AgN or O3. So with practice, I think now with the amount of examples that we have done, all of that should not be a problem. But just in case if you are ever in doubt, always know that you should look out for cations and anions. So for example, when I'm talking about AgNO3, I'm actually talking about Ag plus NO3 minus. Okay. So when we are talking about cations and anions, you will realize that you will be able to really have a clear idea as to what exchanges should I be really looking at. Okay, similarly in Fe2O3, you will realize that it is the iron and chlorine which can go together, and oxygen and hydrogen can go together, right? So these are a few more examples of double displacement reaction. What are the conditions of double displacement reactions? Most of these reactions will not occur unless they are dissolved in water. Okay, because the dissolution in water actually gives you an ability to separate the ions. So if you are able to separate the ions, you will realize that double displacement reaction is more prone. Then reactions are more likely to take place if one product is molecular compound, a precipitate, or gas. Okay, so this is one more. This is just a trick that I'm sharing with you, that how to really identify whether a double displacement reaction will occur or not. So in the products, if one of them is actually a molecular compound, when I say a molecular compound, it means either it is a very stable covalent compound, or it is a precipitate, or it is a gas. Okay, so in any of these scenarios, you'll realize that you will have the double displacement reactions going forward very easily. I'm going to compare this with our examples that we have seen so far to explain you. So for example, you'll realize that AgCl is a precipitate here. So in this scenario, this AgCl is going to get into the solid state. Similarly, FeCl3 is also a precipitate, and it will be into the solid state. So this is one key to understand that double displacement reaction is possible. Let me give you one more. When you really look at CaCO3 plus HCl, CaCl2 is a precipitate, but H2CO3 also and further decomposes into H2O plus CO2. So CO2 gas is released. Because CO2 gas is released, let me write it for you. So H2CO3 gives out further H2O plus CO2. So as CO2 gas is released, you'll find out that the double displacement reaction is very prominent here. So most of the double displacement reactions will have either a gas or a precipitate being released or put into the system. Now let's look at a few more reactions. The next type of chemical reaction is combustion reaction. Now, combustion reaction is very similar to addition reactions. The only question is that in combustion reaction, oxygen definitely gets added. So, you will find that in combustion reactions, sometimes, a combustion reaction can have an addition happening between them. Okay, so an addition reaction is sometimes a part of combustion reaction, but not all combustion reactions will be technically only a combination reaction. When I say addition, I'm talking about combination reactions. Okay, so for example, you'll realize that in hydrocarbon plus oxygen giving carbon dioxide plus water, you will realize that oxygen is getting combined with carbon and hydrogen, both of them. Okay, so let me give you another example. So for example, we have C2H6 giving O2, the same reaction that I'm talking about, CO2 plus H2O. Okay, so we have carbon dioxide plus water getting released because of oxygen getting added to the hydrocarbon. Okay, so this is the most commonly used combustion reaction. You'll find that this being mentioned in a lot many places around around your text. The second one is with fluorine, for example. You can have the same C2H6 plus fluorine gas. You can say as F2 or F, giving you carbon fluoride, which is CF4. Okay, plus hydrogen fluoride, which is HF. Okay, so these reactions are also sometimes mentioned in your text quite commonly. So the products of oxidation of hydrocarbons in normal conditions is carbon dioxide and water vapor. Okay, so these are all combustion reactions. So combustion reactions are a typical type of combination reactions. Okay, so that's something that you can actually really look at. Now let's look at some more examples. For example, you have this as hydrogen sulfide. You find that when it reacts with fluorine, it not only gives you carbon fluoride, but also gives you hydrogen fluoride and sulfur hexafluoride, right? So similarly, here you are finding that methane with water is actually and nitrogen is actually not only giving you CO2 plus H2O, but also the nitrogen comes out back and heat. The nitrogen generally used here to actually keep the temperatures low or really have a smooth reaction within carbon, methane and the oxygen molecule. Okay, so these are a few examples of combustion. Please note the way the heat is written here. So which means that as the products are produced, heat is given out. Okay, the next is not all of the reactions that you will encounter in your chemistry syllabus, even in the next 4 chapters, which we'll look in a few days, are actually of the 4 types. So they some of them actually are for example, also redox reactions, some are neutralization reactions. So there are multiple classifications that we look at, but these 5 classifications are very prominent in your first chapter, that you need to know about in terms of their definition, their examples, their form, and their principle, the reason why they write. So I'm going to write these 5 points for you on this. So anytime that any of these reactions are asked to you, the first thing that you need to do is you need to write its definition as the first point. The second point, you need to write it as the general form that it has. For example, I've given you all the general forms of these reactions. The third thing that you can actually write is the reason that they do. For example, either it is the reactivity series, or it is simply because of oxygen getting combined. So all of that, the reason is very important. The fourth you can always write is as an example of this chemical reaction. Balance the examples pretty well to write the chemical equations of all of these, right? So these are the four major points that you can always write for any of these examples of chemical reactions. Now let's look at the other types of mentions in your text. So for example, redox reaction is something that has been mentioned quite commonly in your textbook. So what is a redox reaction? Redox reaction is a combination of oxidation and reduction reaction happening together. In simple terms, what is an oxidation? An oxidation is where oxygen is added, or hydrogen is removed. Okay, or hydrogen is removed. So this is the most common definition of oxidation. Uh, Now, whenever an oxidation happens in a reaction, reduction has to happen. Of course, when someone gets oxidized, only then something will get reduced. There is a question by Param who says, "Sir, if the nitrogen isn't reacting, why do you need 7N2 and not just N2?" That's right, Param. The answer for that question is basically the nitrogen here is just being used as a coolant. Why 7 nitrogen? Because that's the proportion of gases that you generally keep in the container, so as to have an effective a transfer of heat. So not that the nitrogen is a part of the reaction. I wouldn't recommend that you really really pick this up as a very special example, but I would just say that it's basically a ratio of gases that is being used, so as to there is a effective transfer of heat between them. It isn't it acting as a catalyst? No, it's not acting as a catalyst. It's simply acting as a coolant in the reaction. So we don't need any catalyst to burn methane. It's just simply a coolant. So coming back to our answering that question, we come back to our definition of redox reactions. So in redox reactions, you'll find that one of them actually undergoes oxidation while the other goes reduction. So you'll realize that in CuO, here is getting reduced because oxygen is getting removed from CuO to give you copper. So this is an reduction reaction, whereas hydrogen is one which is getting an oxygen. So this is an oxidation reaction. Now, when both oxidation and reduction are happening together, you'll realize that this reaction is called as a redox reaction. The very word redox comes from red and ox, which means reduction happening with oxygen to oxidation together. So that's the way that this works. Sai Vidya is saying, "Sir, in the reaction Cu plus O2, there is only oxidation." Well, no, Sai, basically the hydrogen taking in oxygen is also termed as oxidation. Okay, so this is very well an oxidation. I know the common question that might be coming to your mind is, "Sir, but isn't hydrogen also getting added to there? So how do we call it as oxidation?" See, technically, when CuO gets reduced, the one that makes it get reduced will get oxidized. So what for where we call this as reducing agent or oxidizing agent. So if I have to really look at, hydrogen here is our reducing agent for CuO, because H2 is reducing CuO to give you Cu, whereas if you really look at CuO, it is the oxidizing agent for H2, because it is actually giving hydrogen and oxygen to get oxidized. So we will mention this as oxidation of hydrogen, whereas reduction of CuO. Uh, yes, so the above reaction, yes, eventually gets CuO. That's right. Yes. So yes, so you're right, Sai. So that as I mentioned, yeah, eventually as copper gets reduced, it ends up getting copper, and hydrogen gets oxidized to water. So that's a part of redox reactions. If you have any questions on this, please shoot it out on the chat window, and I'll be happy to answer them. Let's look at the last part of our chapter, which is parts of corrosion and rancidity. In another 10 minutes, I'll be taking up a free discussion on all the questions that you have on this chapter once we finish this presentation. So the last two parts of this chapter is corrosion, which is special definitions that have been mentioned in your syllabus. The idea of corrosion is it's the process in which metals are slowly eaten up by the action of air, moisture, or chemicals. Okay, now please note we have explicitly mentioned here air, moisture, and chemicals. For example, rusting is a form of corrosion. Now, rusting is just one form of corrosion. Uh, Vikas is asking, sir, are neutralization reactions redox reactions? Because no, in fact, in neutralization reactions, there is simply double displacement reactions. So we have seen this earlier as well. I'm going to give you an example. For example, if you really see NaOH plus our very common example of HCl giving NaCl plus H2O. You see in this scenario, no one is getting removed of only oxygen or only hydrogen. When you're taking out OH from sodium, you're taking out oxygen as well as hydrogen. From chlorine, you're actually taking out hydrogen and putting up another electropositive element. So that's really again not a reduction. So neutralization reactions may not be redox reactions. Okay. Uh, uh, so there could be a few cases where they might have oxidation reduction happening, but in general, it's not a thumb rule that all neutralization are reductions. So not necessary. Uh, yeah, coming back to our corrosions. So corrosion basically is a process where metals are eaten up slowly by the action of air, moisture, and chemicals. For example, rusting is a form of corrosion in which iron is eaten up. Okay, so this is one corrosion where we only talk about iron. For example, we also have corrosion of aluminium where aluminium oxides are getting formed. We have corrosion of silver where silver halides or silver oxides also are getting formed. So those are different types of corrosions. Rusting typically is a type of corrosion where we speak about iron and the action of air, moisture. Also reddish brown coating of iron oxide is formed. Okay, so remember the color. The color is important of iron oxide. The reaction for iron rusting is given generally in terms of Fe2O3 as is mentioned in your text. Please, I've also seen people writing Fe plus oxygen giving FeO. Okay. Ideally, this is not really a wrong equation, but I would recommend that you stick to the Fe plus 3H2O to Fe2O3 plus 3H2 reaction. This is because iron is most stable in its highest oxidation state, which is plus 3. So where it actually forms Fe2O3. So this is the recommended reaction to write for corrosion, especially rusting of iron. And whenever you write example, please take a note of this as well. Now, how do we really avoid corrosion? We have discussed multiple methods, but I'm going to talk about four most prominent methods that are important for you. One is painting of metal surfaces. So we paint with with either an oil paint or something that can cut the contact of the metal from air. So this the idea here is to the contact has to be lost with the moisture or air so that the rusting is avoided. Second is we do powdered coating of surfaces. So basically what we are doing is we are putting in either some ceramic material or we put in some other element which can also be coated on other elements so that they actually lose the contact with with the air or with moisture, and therefore rusting is avoided. Now the other important thing is we can oil the metal surfaces. So this is something that we also do. For example, in our bicycles, when we put grease or oil on the chain, one of the reasons is to really lubricate it, but one also important reason is to actually keep them from rusting, because rusting are going to make their strength weak. The chain is going to get weaker, and therefore it will be useless after a certain amount of time. So that's oiling method for metal surfaces. The last method is galvanization. This is actually applying a protective layer of zinc over iron or steel. There are two reasons for this. One reason is, of course, zinc being more reactive than most of the metals. It sacrifices itself when it comes to rusting. Okay, so it will sacrifice itself and not let the metal really get weakened. So that is one reason. The second reason is, of course, when zinc coating is there on iron or steel, it is the zinc which is in touch with the moisture, and the iron and steel are actually avoided a contact with moisture. So of course this is the common reason that why we do any kind of electroplating for that matter. So these are the two reasons that we do galvanization for. uh, and Yeah. So this is one. Then coming back, so there is a question from Sai, sir. Can you explain, even after zinc coating is broken, the article is still resistant to corrosion? Is it something to do with oxidation of zinc? I just mentioned, Sai, about that. So even after you break the zinc coating, the article is still resistant to corrosion, because you have just broken the zinc coating, but unless you have really taken out zinc out of it, zinc will be the one that will be the first to take away any moisture that is there. So H2O or oxygen or any other gaseous impurity that is going to come in. And the reason for this is zinc is more reactive than than most of the metals. Most of the metals which are solid, for example, iron, steel. In that scenario, zinc will sacrifice itself against any of these metals. So when we say that the coating is broken, we don't mean that the coating is completely removed. The question simply means that, let's say you have a metal container and everything was coated with zinc, but now you have a gap in it. Okay. So even when there is a gap, and if there is moisture that is now touching the inner metal element, why is the metal not getting corroded? And the reason for that is, even if moisture is coming in and the metal is wanting to have a reaction, it is zinc who will react faster than the metal. And you'll find that zinc will sacrifice itself to protect the metal covering. So that's the reason for zinc being used quite often to coat very highly sensitive instruments, especially iron instruments, and it saves the iron from getting corroded further. Right. So that's a quick recap on corrosion. Let's look at rancidity. Now, rancidities happen. Rancidity basically happens when food substances mostly, which contains oils and fats, when they are exposed to air, they get oxidized, and when they get oxidized, they end up giving out foul smell. Their taste also changes. Sometimes it's bitter, sometimes it's simply pale tasting, stale tasting, and that's also the word stale comes from. And there is also a color change. A classic example is apples and bananas. When they turn rancid, they actually are unedible. So so how we define rancidity is, when substances containing oils and fats are exposed to air, they basically get oxidized, and they form tasteless, foul smelling and colored substances. This process is called as rancidity. Please note, the process is rancidity, okay, and the objects are rancid objects. So when rancidity is mentioned, do not say that apple is rancidity. I've read these answers. That's wrong. The process is rancidity. What substance is formed as a is called as a rancid substance. Okay. One of the examples that I have mentioned here is, when butter is kept open for a long time, it starts smelling and its taste changes. So that's also one of the reasons that we keep butter either in a refrigerator or it's covered. Okay. So that's rancidity. Now, how do we avoid rancidity? Rancidity can be again avoided by a couple of methods, 5 different methods I have mentioned here. One is that it can definitely be prevented through antioxidants, which means that substances which prevent oxidation of food. Okay. So that's one. The second is, you can also store this in airtight containers where air does not come in and really mess up with the food substance. So you will find that you put them in airtight containers, and this avoids the process. It may not completely avoid, but it slows down the process of rancidification. It's called as rancidification. And you can have longer shelf life of the food products. When I say shelf life, it means how long can I store a food product without any external support. But if you need to take an external support, then refrigeration is the best idea to go for. So you put in refrigerators, which also slows down the process of rancidification. If you cool it at the right temperatures, you can really delay rancidification for a very long time. And The last one is to replace oxygen in the containers with another gas. For example, you can use nitrogen gas. Any inert gas would be sufficient, but technically using directly inert gases is not really feasible. So therefore, nitrogen is the best one, which is quite inert and can be used in multiple usages, and can help us in storing these substances for a very long time. So these are the different ways, 4 different ways, as to how do you really avoid rancidity. um, Yeah, so that brings us to the end of our revision on this chapter, and we have covered all the important points, as well as we have seen how do we do answer writing, and we solve all of these numericals and questions. Now I would like to take in the questions that you might have on any of these topics. Okay, so I can answer you all of them now. Please feel free to post your questions, or I'll be happy to take them one on one as well, if required. Yeah, yeah. So if you have any questions, feel free to mention them uh, on the topic. Yeah. Yes. So Param says, why does refrigeration delay rancidity? Good question, Param. So firstly, for any chemical reaction to happen, having a minimum amount of energy is very important. Okay. So let's take an example. Let's take the oxidation example itself. So let's say you have a compound which is ethyl alcohol, and this alcohol gets oxidized. When I write this in oxygen, it means that it is getting oxidized to, let's say, CH3 COOH. Okay, which is, so when ethyl alcohol is oxidized, it ends up giving acetic acid. Now this oxidation basically happens because now some bonds are broken. Of course, the CH bonds in ethyl alcohol are broken, and new bonds are found between carbon and oxygen. Now the question here is, to break these bonds, I need some amount of energy. So what we essentially do is, in refrigeration, we are bringing down that energy of the particles, and when we bring down this energy, the reaction is not feasible in the same amount of rigorousness that it is needed. So any reaction happens because of collisions, right? So when these oxygen atoms would collide with these particles, they need certain amount of speed, kinetic energy, so that they can actually knock off these hydrogens or break these bonds, and then get converted into an acetic acid molecule. But in our situation, when we are refrigerating it, we basically are taking away temperature from them, which means we are trying to take away the thermal energy. And as we take out thermal energy, the kinetic energy is also reduced. So the collisions are which result into a change of reactants to products are lesser, and therefore reaction slows down. Now please note that this is not the case for exothermic reactions. So if you have a reaction which is actually giving out heat and getting more stable, if you bring down the temperature, these reactions get accelerated. Why does that happen? That happens because the reaction is more favorable when there are low temperatures, because the reaction themselves is giving out heat. So if the surrounding is not opposing their expulsion of heat, then they are more comfortable in giving out energy. But if the surrounding itself has a high amount of energy, then the surrounding is going to suppress the evolution of heat for them. So this is a separate topic from what your question is, but the idea is that the refrigeration process really works for those compounds which are actually endothermic, which need energy to really go forward, right? So if you don't need energy to go forward, refrigeration does not help. To give you some examples, is that you've seen that some of the food particles, even after refrigerating, do not stay for that long. A classic example is actually flesh. You'll find that vegetables and themselves still have some amount of shelf life, but flesh and all actually, sometimes some amount of flesh actually degrades faster than even a few vegetables, for example potatoes and all. So yeah, different substances have different abilities to react in terms of the energies that are required. Yeah, so that's one question. Maybe any other questions that you might have? Yeah, please keep on shooting, since there is a small time lag between what you type and where I answer. So it's a good idea to actually keep the typed questions out there on the chat window, so that once I've answered a particular question, then I'm free to take up the new one. Sir, is refrigeration also because of bacteria? uh, what do you mean by that, Rushir? You're saying that bacteria, the bacterial action is suppressed because of refrigeration? If that's your question, then the answer is yes. Again, but the point there is the same. Even for bacteria to do a chemical reaction, need energy, need at least some amount of kinetic energy for the molecules to combine. So what basically bacteria do is they end up secreting some chemicals which help the reaction. But the other thing is also for bacteria to really survive, there is certain amount of temperature that is needed. But if you really drop the temperature, then bacteria cannot survive in that temperature, or less amount of temperature can really be detrimental for bacterial action. So yes, that actually can be something that does not help their action on the chemical substances, and therefore rancidity can be avoided. Yes, so that's one reason. So that's true. Okay. Right. So any other questions that you might have? Uh, if not, I would like to give you a couple of questions. But I would like to wait for, because more than me testing you, this is a time where if you have really practiced, and if you have anything to ask about, you can actually ask up. Yeah. Good. So yeah. So since I don't see any more questions coming in, I would recommend you guys to have your textbooks handy and just skim through them. If you feel that there's anything that you need to ask, you can ask that. But if there's nothing, then what I would do is I would like to give you some questions myself. Here's a quick question, an easy one, but maybe I just would like to you guys to really write it. So I'm going to write this as uh, borane when. So this is a word equation. Question is Param, I would suggest that we just discuss about chemical equations and chemical reactions for today. If you have a question, you're most welcome to put it out on the personally to me on WhatsApp, maybe after the session. But for the time being, I would like to focus on chemical reactions. If it is connected to the topic, I would be happy to take it up. Uh, yeah. So let me write you a question for here. When is put in water, borane is put in water, BORANE is put in water, uh, it gives out boric acid and hydrogen gas. The question is, please write a balanced chemical equation in entirety for this expression, this word equation. I'll wait for about 30 seconds, and I would be happy to really look at your answers in the chat window. Yeah. So while others are really looking at the solution for this, I'll be answering Param's question. So yeah. Meanwhile, I think people are also trying this. Yes. So till others are attempting. Yeah, that's why Ruchir I asked this question. So yeah, just try and attempt. I know that you might not know the chemical formula of a few compounds, but that's the reason that I wanted to give this question. So try and attempt this. I'll give you a solution in a few minutes. Okay. So psi says BH3 plus H2O giving H2 plus BH2O3. That's a good attempt, Sai. I think you have got half of it right, but you've made a small mistake. Uh, but we'll look at that. We'll look at that in a few minutes. Yeah, so that's a good idea. I'm going to share this solution with you because I imagine, yeah, I imagine that you guys are slightly behind me in terms of this so recording. So borane actually is BH3 and diborane is B2H6. Okay, diborane is B2H6 and BH3 is borane. Okay, generally borane exists as diborane. Okay, I mean commonly in the chemical world. But if they have given you borane, it's you should take BH3. So BH3 plus H2O. When you say boric acid, it is actually H3BO3. So Sai, you had given a right good answer, but instead of H3BO3, you mentioned H2BO3, which is slightly different, plus H2. Okay, so this is the now H3BO3 is aqueous, obviously, and you have H2O liquid, and you have BH3. Diborane is actually gaseous in nature, so I'm going to write BH3 also gaseous. Okay, so I'm going to choose this as the gaseous form. Now let's understand how to balance this. Now you realize that the OH is all the time getting displaced. You'll find that probably it's already balanced. Okay, so there is 3 hydrogens here, 2 hydrogens here, 5 in total. Again 5 hydrogens, 1 boron, and oxygen is just not balanced. So oxygen is yet to be balanced. So I can really put 3 here. So the moment I put 3 here, I will put another 3 here. So now let's see. This is 6H2. There is 6H2. 3 oxygens are balanced. Boron is balanced. And so this is yeah. So this is 6 plus 3 9. There is another 6 plus 3 9, and so everything seems to be balanced now. So borane is BH3. This is water. This is H3BO3, which is boric acid, and H2, which is hydrogen. Good. Now, let me give you one more question on balancing the chemical reactions. Let's say if, iron 3 oxide, Fe2O3, or plus carbon monoxide. Okay, predict the products, predict the products, and balance the chemical equation. So this could be a bit simpler. See if you are able to predict the products and balance this chemical equation. I'll pause for a few minutes one more time. Yes, so how many of you have got this? Can you please post your solutions in the comment box? Okay, so it seems a few of you have attempted it already. Let me see. Okay, so I'm going to give you an answer for this. So this actually ends up giving Fe metal. So please remember, whenever CO is a part of the of the uh, equation, CO will always end up going to CO2. Okay, CO is a very good reducing agent, and it ends up going to CO2. Yeah, so Param has got it right. Ishan, you've It's not iron oxide, it's actually iron plus CO2. Okay, so I'm going to give you this reaction, that is Fe2CO3 plus CO gives Fe plus CO2. Yeah, now the only thing that, yeah, perfect, I think Shubham has already balanced it, and Shubham has got it right as well. Okay, Shubham, that's perfect. So you end up getting Fe2O3 plus thrice of CO gives twice of Fe plus thrice of CO2. Very good. I think that's a good answer. Yes, Shubham's is correct, and Param, I think you've just not balanced it. I think rest was right. Ishan, FeO is not the product. When CO is present, CO will generally try to take out everything, every oxygen bit. If you remember, CO is also used, not just CO, but carbon is also used in the smelting process, which we have seen in metals. Okay, so the very reason that we use the smelting process is because carbon actually really make carbon actually takes out every oxygen that is possible and makes things happen. Okay, so Fe2O3 plus thrice of CO gives twice of Fe and 3 CO2. That's correct. 6 and 6. Yeah. So oxygens are balanced, carbon is balanced, and iron as well is balanced. Perfect. I think that's a right answer. Now let me ask you one more question. Okay. Let's say. Uh, hmm, okay. So I'm going to ask you a multiple choice question, and try and answer these questions, okay, as much as possible. So here is a reaction which I am giving you. Cu plus XHNO3, okay, gives CuNO3 twice plus Y times NO2 plus twice of H2O. Okay, your question is, what are the values of X comma Y? What are the values of X comma Y? So try and get these values ASAP, and let's see what values do you arrive at. Okay. So Sai mentioned some answer. Let's see about others. Okay, so now Sai thinks probably is just not, is still wanting to try. Let's see. Okay, so a lot of people have given the answer. That's right. It's 4 and 2. You're correct. So let's look at how it really works, right? Now, one good idea of this question is that they have already given you a balanced hydrogen. If they would have not given you hydrogen balanced, then it would have been a much more difficult question. But the moment hydrogen is balanced, the idea is that X has to become 4, okay, because there is no other hydrogen component that is there in the reactant side. So, and there is only one hydrogen component on the product side. So this definitely has to be 4. Now, the moment this becomes 4, let's see what really happens to nitrogen. You see, nitrogen are 4 here. There is only 2 nitrogen here. So definitely this has to be 2. Now, when we take this as 2, let's see whether we are able to balance oxygen, which is the key question that we have to answer. Copper is already balanced. Here we have 12 oxygen on this side. Now, on this side, we have 6 oxygen here. Now, we need 6 more oxygen. When we write this as 2, we only end up getting 4 oxygen here. But there are another 2 oxygens that come in from this side, and therefore this ends up again to be equal to 12 oxygen. Please note, had this 2 not been given, this would have been a tougher problem. So maybe in the next question, I would try and really keep this also as a hidden one. But let's see what how this really evolves. Now, good. So a good answer. I think everyone could get this. This is a good attempt by all. Okay. Now let me give you one more question. Now, here's a question that I'm going to ask you, and please note that I'm going to mention this verbally, so please pay attention. Which of the following statements is not correct? Okay, so I want which statements is not true or not correct. Okay, now the first is chemical equation tells us about the substances involved in a reaction. Okay, so it is talking about chemical reactions, and it tells us about substances that are chemical reactions, substances that are involved in reaction. Okay, substances involved. Okay, so this is the first statement. The second statement is, and please note this is a multiple correct option, so one might be correct, all three might be correct answer. Please note you have to find which is not true. Okay, now the next is a chemical equation informs us about the symbols and formula of substances involved in a reaction. So it is saying that chemical equation informs us about the symbols as well as the formulae of substances involved in the reaction. That is point B. Okay. Point C is a chemical equation tells us about the atom or molecules of the reactants and products involved in a reaction. So they are saying a chemical equation tells us about the atom slash molecules of reactants and products involved in the chemical reaction, of reactants and products involved in the chemical reaction. And the last option is a chemical equation represents energy changes. It represents energy changes in the chemical reaction. In the chemical reaction. Okay. Now please think, guys, this is quite close. Okay. I'm asking you which of this is not true. I'm going to repeat all the 4 statements. There are some keywords that I've written on your screen. Please think about it and answer wisely. The first is chemical reaction, a chemical equation tells us about, so this is a small correction here. This is chemical equations that they're talking about. Chemical equations tells us about the substances involved in a reaction. The second one is chemical equation informs us about the symbols and formulae of substances involved in the reaction. The third one is chemical equations tells us about the atom or molecules of the reactants and products involved in a chemical reaction. And the fourth one is a chemical equation represents energy changes during a reaction. So you have to tell me which one of this is false or not true. Okay, so I'm getting some answers. So a few of you are saying, sir, D and C not correct, C is false. I think 4 is not necessarily true. 4 is all that you are talking about. Someone is saying that C is also not true. Okay. Any other answers? Okay. Okay. So the answer, Can energy changes be related to physical states? That's right, Sai. But in energy changes, we are actually trying to understand what is the amount of energy released, how fast it is released, by how many substances. So to give you, I think most of you have actually guessed this. So this definitely is wrong. Okay, so it definitely does not tell you. It can tell you whether heat is released or not, but how much heat, how fast, by how many substances, all that is not mentioned. So energy changes in a chemical reaction, definitely a chemical equation does not represent. Now let's look at the others. Does a chemical equation tell us about the atom or molecules of the reactants and products involved in the reaction? No, it does not. Please note, it does not. Why? The reason is, unless we write it in the ionic form, for example Na plus plus Cl minus, I don't even know whether Na and Cl are covalently bonded or they are ionically bonded. So it does not talk about any atoms per se. It does talk about molecules, but it does not talk about atoms. So this option also is wrong. Okay. So Pratyush says, but sir, energy has to be necessary in chemical change. Yeah, that is right, Pratyush. But as I mentioned, we only talk very broadly. We don't say whether 240 kilojoules and how fast it happened, and how was the form of energy change, whether it was only heat or whether it was light, or so there are multiple information that you can derive out of energy changes, and not all that information is represented in the chemical equation. So therefore D part definitely is not true. Yeah. Then Vikas is saying, sir, but it tells us number of atoms. Yes, you're right, Vikas. But the point is, another few information about atoms is not said. For example, I gave you an example of NaCl. It tells you the number of atoms, but the information is not complete, right? So when we are saying that chemical equation tells us something, it means that it should be a complete information, right? Because the statement is incomplete without we having some information missing in the expression. So therefore, it tells us about molecules. If you tell me that, does it tell us about NaCl, whether it tells us about its state, whether it tells us about whether it was dissolved or not and what happened to it? Yes, it does tell us about molecules. But about atoms, what is happening inside the molecule, we really do not have enough idea. So the C is also not really correct. Now the B1 chemical equation informs us about the symbols and formulae. Sir, what did the option say? Yeah. So the option says this. I'm going to read the C option one more time. A chemical equation tells us about the atom or molecules of the reactants and products involved in a reaction. So it does not tell us about the atoms. It definitely tells us about the molecules. Unless it is in the elemental form, it does not talk about the atoms. So there is some ambiguity that we really see in there. Okay. So that's one more point. Let's look at the B1. A chemical equation informs us about the symbols and formulae of substances involved in a reaction. Actually, it's not chemical reaction which talks about formulae. It is the formulae which talks about chemical reactions. So it is the other way around. Okay. So for example, if a reaction is written, the very same reaction, let's take NaCl plus H2O, hydrolysis of salt, giving back NaOH. Okay, so this is called as the hydrolysis of salt reaction. If this equation is written, this equation is based on the formula, but if I'm getting the formula itself wrong, if I write this NaCl2 plus H2O, then the chemical reaction does not help us in understanding anything about the formula. Okay, if your formulae are right, chemical reaction will help us in understanding how the equations really changed. So to your surprise, the option B also is not correct. Okay, please understand this. I'll reread this and I'm going to explain you this one more time. A chemical equation informs us about the symbols and formulae of substances involved in a reaction. It is not the chemical equation who tells us, it is the formulae who tells us about chemical equation. So if we have the formulae right, then the chemical equation is right. If I write any chemical equation tomorrow, for example, if I write this as NaCl2 plus H2O2 giving something else, it's not going to tell me whether this is the symbol of this is the molecular formula of any compound or not. It might be absolutely wrong. Okay, so it's not the chemical equation which tells us, it is the other way around. The first one says the chemical equation tells us about the substances involved in a reaction, which is true. In chemical equations, we do write the substance name. So only first option is correct. All the other three is is wrong. And the answer is very close. If you really observe this discussion, you'll find that the answer was pretty close to understanding which was right and which was wrong. So be very careful when you do all of these, right? Now, we are just nearing to the close of the time. So I just want to pause here for another minute, and I think there is a good amount of discussion that we could do today. Uh, the similar sessions will be happening all over the entire month, and we will be doing the entire crash course for the upcoming time. What I would like you to suggest do is the schedule of the crash, this revision course. is being shared with you, so I suggest a couple of things that you should really look at before you attend these sessions. One, it's a good idea to send me your doubts beforehand, okay, so that I will compile them in the presentation itself and do that. The other thing is, it's also a very good idea to study the topic and be ready for the topic, because if you do that, then it would be much more uh, convenient for us to really share information, and it will be a kind of a much more reinforcement of what you have already studied. So that's a very important point, that you study the topic and attend these sessions. The third one is, after the session happens, please go and solve all the previous year's question papers on this particular topic that we are doing. Please note that all of these sessions are happening not only for chemistry but also for physics, for maths. So if you're attending the previous year's question papers right after these sessions, that is going to be the best method for you to really consolidate on the complete understanding of all the topics of all the chapters. So I would be very strongly recommending that you do that. The drive link is already shared with you, by Rohit sir, Tushar sir. So please feel free and use that to your maximum benefit. If you get stuck somewhere, come back. The last and most important point that I would like to mention is, I have been mentioning what errors happen and how to write model answers. Also, there will be small videos that will be shared on YouTube on problem solving. Please go through them and make sure that your answer writing ability improves. I think this is a time where you have enough information with you, but your answer writing ability is something that is very, very important to go forward. Um Rushil, this schedule is actually fixed not just for one section, but it's across all the sections for multiple students. So the schedule is kind of stringent, where we'll have to do it the way that it has been planned. But having said that, you can always reach out for individual doubts. Now is the time that you study and you ask questions rather than just listening to the lot of theory around. Okay, so good guys. I think it was a good session. Feel free to stay connected, feel free to ping anytime that you need, and I'll be happy to answer your questions whenever possible, as and when time permits. Okay, so I look forward to seeing you again in the next session, chemistry. Till then, you have a good time, and study hard, work hard. All the very best to you. Make maximum of your time in the coming days. Thank you so much. Yeah, stay well, take care, bye bye.